Okay, so let me go ahead and open this. All right. Okay, so I basically have no plan other than you guys tell me what you would like me to review. Number three? Sure. Okay, so here we're doing the limit as x is approaching infinity. Now, whenever we have a limit where it's either approaching infinity or negative infinity, we would typically divide everything by the highest degree from the denominator. Now, in this case, our denominator is a trig function, so we can't really determine what the degree is right now, or really there's not much for us to divide. So instead, just think about what would it look like if we were to plug in infinity. This would be negative 2 times infinity over cosine of 1 over infinity. Now, what is 1 or anything over infinity going to equal to? If you think about what that limit would approach. 0, exactly. So this right here, this 1 over infinity is the same thing as saying 0, because 1 over a huge number is going to be 0.0000 whatever, right? So this is going to equal to negative 2 times infinity over the cosine of 0. And what is the cosine of 0? 1. Exactly. So this is negative 2 times infinity over 1, which if you think about it, a negative number times infinity is just going to be negative infinity. And that would be your answer. Okay, what's next? 13? Sure. Okay, the limit as x is approaching 0 from the left of the absolute value of x over x. Now, whenever you have a limit of absolute value, I know that this was like a long time ago, but basically you have to create the piecewise function that represents that absolute value. So if I were to do that, this right here, the absolute value of x is equal to the piecewise function where where the absolute value of x is just x for when x is greater than or equal to 0, right? Because it doesn't matter what positive number you plug in, since its absolute value of a positive number, it's still going to be that number, right? But it would be negative x if x is less than 0. Do you remember this when we did this a while back? No? Okay. This I would review. I mean, if you get an absolute value question, it'll be like 1, maybe 2. But basically, what you do is you take the absolute value, you remove the absolute value bars, right? And for it'll be that where x is greater than or equal to 0. And then you apply the negative to whatever is inside the absolute value, and that would be for when x is less than 0. That kind of sums it up. Is that okay? So since this is for when x is approaching 0 from the left is this bottom part of that piecewise function. So what we do is we replace the absolute value with negative x. So this is the limit as x is approaching 0 from the left of negative x over x, which here the x's would cancel and we're left with just the negative, so negative 1 would be our answer. Is that okay? Yeah. Okay, so if you have the absolute value of x plus 4, then to create the piecewise function, you remove the absolute value bars, so x plus 4 is greater than or equal to 0, right? And then you would solve for x. So this would be x is greater than or equal to -4. And then for the opposite version, you just basically switch your sign. So it would be x is less than or equal to -4. Sorry, less than -4. So that would be basically, it's this, sorry, it would be x plus 4 for when x is greater than or equal to -4. And then it would be negative x minus 4 for when x is less than -4. You see how I applied the negative and then switch the sign here. Okay. What other questions do we have? 53, is that what I heard? Okay, let me open it up here. Okay, a rectangle has its base on the x-axis and its upper vertices on the parabola y equals 12 minus x squared. What is the largest area that the rectangle can have? Okay, so this is optimization. This is asking for the largest area. So it tells us that there is a rectangle on the x-axis. Typically, when they tell you things like this, it's like, unless otherwise specified, the rectangle goes through the origin and you have the same space on either side. So this would be, let's say, my rectangle. Is that okay? Then it's a parabola, which is 12 minus x squared. Now, when you look at this equation, right, this is typically not a calculator question, but because the x squared has a negative in front, that means that the parabola is facing down. Is that okay? So it would be like this. That's your parabola, and then that's the rectangle that is underneath. Especially since it says that it has a base on the x-axis, so here's the base on the x-axis, and its upper vertices, which are these here, on the parabola. So you can see that it's on the parabola. That's okay? So the area for this rectangle, the area is the base times the height, right? Now the base here, we have x and x. So the base would be 2x, right? Because x plus x is 2x. And then the height, which is the parabola, is just y. So 2xy. Is that clear? Now here in the question, they tell you that y is equal to 12 minus x squared. So what we do, since we want to maximize this, we have to plug in, because we have too many variables here, and when we're maximizing, that means that we're going to take the derivative and find that critical number. What we do is we're going to take what y is equal to and substitute it in here. So this is 2x times y, which is 12 minus 2x squared. 12 minus x squared. So far, so good? Then we distribute the 2x, so we get 24x minus 2x to the third. So this is my equation for area. Yep. To maximize, we have to find the derivative and get that critical number. So a prime is going to equal to 24 minus 6x squared. And we make it equal to 0 so that we can solve for x. So you would have to now subtract the 24, so negative 6x squared is equal to negative 24, divide negative 6, we get x squared is equal to 4, and then square root. So we get x is equal to plus or minus 2. Now both of these are critical numbers. However, remember that x represents like that length on the bottom of one of these here, right? So because it's a length, it can't be negative. So x is equal to just positive 2. That would be our critical number. Is that all right? Now you can always test this, right? So to make sure that it is indeed a maximum. Here's my derivative. So let's say if I plug in 0, you would have 24 minus 0, which is positive. And if I plug in 3, it would be 24 minus 3 squared, which is 9, times 6 is 54. So 24 minus 54 is negative. So it is indeed a maximum. Okay, so x is equal to 2 is where we have a maximum. But the question is asking for what is the largest area. So we have x. Now we had the equation for area, which is here. So we just plug it in. So A is equal to 24 times 2 minus 2 times 2 to the third. 24 times 2 is 48 minus 2 to the third is 8 times 2 is 16. And 48 minus 16 is 32. So this would be our maximum area. What other questions do we have? Yeah. Find the, okay. So here we're just going to integrate. Let me come over here. Okay, so what I did here is I rewrote this so that it would be a polynomial type function. So how we do that is we need to rewrite this integral first. So this is the integral of x to the 1/2 plus 2x to the negative 1/2. Is that okay for the inside? And then because this is squared, that means that we're multiplying it with itself. X to the 1/2 plus 2x to the negative 1/2. So far, so good? Okay. Now we're just going to multiply. We're going to like distribute this. Remember when you're multiplying, what you're doing, because these all have the same basis of x, all you're actually doing is adding those exponents. So even though they're fractions, they all have a common denominator. This will be easy to add. You get what I'm saying? So if I distribute this x squared, what we get here, x to the 1/2, not x squared. X to the 1/2 times x to the 1/2, that's 1/2 plus 1/2 is 1. So this would be x. Does that make sense? Then x to the 1/2 times 2x to the negative 1/2, 1/2 minus 1/2 would give you 0. And anything raised to a 0 exponent is 1. But we have the 2. So this would be plus 2. Does that make sense? Or if the exponents, I just realized something. If the exponents are confusing, right? Just think about it like this, right? Square root of x plus 2 over the square root of x. This may be actually easier for you to actually see. It's squared, right? Square root of x times the square root of x, the square roots cancel, x. Yeah? Then square root of x times 2 over the square root of x, those x's would cancel out, so it would just be plus 2. Is that a little easier to see? Okay. Then here, same thing. 2 over the square root of x times the square root of x. Those square roots of x's would cancel, so another plus 2. And then here, 2 over the square root of x times 2 over the square root of x would be 4, right? Because you multiply numerator with numerator, denominator with denominator. So square root of x times the square root of x is just x. Does that make sense? So I'm going to scratch this out. Is that okay? Because I feel like this was actually a little bit easier. I don't know, in my opinion. So then what this gives you is x plus 4 plus 4x to the negative 1. And now we can integrate this. Yeah? Okay, so when we integrate x, that would be x squared over 2 plus 4x plus, now here, if I add 1 to the exponent, I get 0. And then I can't divide by that new exponent. So what is this 4x to the negative 1? 4 ln of x, that's right. Or any time that you integrate and you get ln, whatever is inside of ln, put it in absolute value. Okay, that's just a rule because the ln of anything is undefined if it's less than 0. So we put absolute value to indicate that it has to be greater than 0. And then, of course, the plus c. So remember, anytime that you have something that looks like this, a number over x, that's always ln. Okay? Okay, what other questions do you have? Yes. Right here. Okay. A person that is 2 meters tall walks directly away from a street light that is 8 meters above the ground. If the person is walking at a constant rate and the person's shadow is lengthening at the rate of 4 over 9 meters per second, at what rate in meters per second is the person walking? Okay, so this is a related rates question because we're given rates and we have all the whatever. Okay, let's set this up. So I like to draw a picture so that it's kind of easier for you to see what's going on. So we have some person, right, that is 2 meters tall. Here's my little person, right, 2 meters. Walking away from a street light that is 8 meters above the ground. So here's my street light, whatever, right? And this is 8 meters tall. If the person is walking at a constant rate, so this person is walking this way, right? Because it says walking away from the street light. And it says the person's shadow is lengthening. So when they tell you that a shadow is, let me see, hold on a second. Okay, when they tell you that a person's shadow is lengthening or whatever, it doesn't necessarily matter which way you choose the shadow is going, but typically it's like this direction, right? Person is walking away. This is the shadow here of the person. Does that kind of make sense? So what I draw here, and I don't know if you can see it, but whenever you're given two heights and they're both obviously vertical to the ground, what this does is it creates these triangles here. You see how we have this big triangle and then this little triangle. Because with related rates, what we're trying to figure out is what kind of geometric like relationship can we use, like equations that relates one quantity to another. That's why it's called a related rate. How can I relate the rate of this person's shadow to the rate that they're walking? All right, so then you assign some variables. Now we're trying to figure out, right, the rate in which the person is walking. This is the person walking away. I'll call that X. Is that okay? And then this is right here, the shadow. I'll call that Y. So we have an X here and then we have the Y here. So those are my variables. So we're trying to figure out dx dt because that's the rate that I'm looking for. Yes? We are given dy dt. That is the rate in which the shadow is lengthening, which is 4/9 meters per second. So far, so good? Yes. Well, remember your shadow, where is your shadow located? It's on the ground. Do you get what I mean? So, whenever you have a situation like this where you have two triangles, what you're going to create is a ratio because what we have here are two similar triangles, right? A similar triangle means that one triangle is going to be directly proportional to the other triangle. So the small triangle is proportional to the large triangle. Is that okay? So what you do is you create, like I said, a ratio of their sides. So it doesn't matter which way you choose, if you want to go from the big triangle to the small triangle or the small triangle to the big triangle, as long as you're consistent. I normally do small to big. So like, for example, this is the height of the person that I know is 2, and then the height of the lamp here, which is 8. So I create my proportion of 2/8. Is that okay? And now we look at the proportions that we're trying to find, right? I'm trying to figure out what x is, or rather dx dt. So I got to create a proportion that uses this x and y. So I went from small to big. So now I'm using the base of my triangle. The base of the smaller triangle is y. And then the base of the large triangle is x plus y. You see what I'm, because since the small triangle is inside of the large triangle. Does that make sense? So this is x plus y. So these are the ratio of my heights, and this is the ratio of my bases. So far, so good? Kind of? Okay. Now, at this point, once we create an equation, what we like to do is then find the derivative. If I find the derivative here, we have the fractions, it's kind of annoying, whatever, right? So before we take that derivative, what we can do here is we can cross multiply to create an equation that no longer has fractions. And that way it could be a little bit simpler when we start taking those derivatives. So with ratios, when you cross multiply, again, doesn't matter if you choose to go this way first or this way, like if you do 8 times y or 2 times x plus y, whatever. Okay, I'm going to do this one here first. So 2 times x plus y is 2x plus 2y is equal to 8y. Is that all right? Okay. Now, to further simplify this, right, I could subtract the 2y from here. So we have 2x is equal to 6y. This is as simple as I can get with my equation. So we started off with this ratio, and the whole point of doing this is to basically simplify that equation to something that is a nicer to work with. And now we take the derivative. Okay, now remember with related rates, our derivatives are always implicit in the sense that when you take the derivative of anything with x or y, it's always dx dt or dy dt. Yes? So this is 2, right? Because the derivative of 2x would just be 2, and then you multiply dx dt is going to equal to the derivative of 6y, which is 6, and then you multiply dy dt. Now we have dy dt, we need dx dt, which is exactly what this equation lets us find, because I can now plug in the dy dt and solve for dx dt. So we have 2 dx dt is equal to 6 times dy dt, which is 4/9. You can multiply this, right? This is 24/9, or you can simplify the 6/9, which can both be simplified by 3. So this is 3, and this is 2, and then I can multiply that, which gives me 8/3. Is that okay? So now my equation is 2 dx dt is equal to 8/3. And our final step would be to divide the 2, which is the same thing as multiplying by 1/2, which this 8/2 can be simplified to 4/3. So dx dt is equal to 4/3, and then our units, which is meters per second, since this is a rate. And that would be our answer. Yes. 39. Here we go. Okay, what am I doing here? Is this derivative? Yeah. Okay. So when you're just taking a derivative when you have both x and y, remember that that is implicit. So when you take the derivative, you have to, every time that you see a y, you would have to multiply that by dy dx. Okay, this is not a related rate, so it's not dy dt. It's all in terms of x, so dy dx. That sounds familiar? Okay, so basically all we do is we take the derivative going straight across. If we have tangent or any trig function, that is a chain rule, right? Because you got to take the derivative first of the trigonometric function, and then you multiply that by the derivative of the angle. So what is the derivative of tangent? Does anybody remember? Secant squared, that's right. So this would be secant squared. And remember, we leave the angle alone, so be xy. Now we multiply this secant squared with the derivative of the angle. Now the angle here is a product, so we have to apply the product rule to xy. Okay, so the derivative of x is just 1, so y, plus, then we leave the x alone, and the derivative of y, which is dy dx. Is that okay? Plus, now we go on to the rest of the equation. The derivative of y squared is 2y, and then you multiply that by dy dx is equal to the derivative of x, which is just 1. Up to here, is that all right? Okay. Now, whenever we're doing implicit, the whole point is for us to solve for dy dx. So what we have to do here is we have to isolate dy dx on one side of this equation, doesn't matter which. They're already both on the left side, so I'm just going to leave it on the left and move everything else over to the right side so that we can solve for dy dx. But first, we have here this dy dx is within this parentheses, so we're going to have to distribute this secant squared so that way we can then move it over to the other side. Do you get what I mean? So when we distribute the secant squared, we get secant squared of xy times y, which normally we would write the variable over in the front. So this would be y times secant squared of xy plus x secant squared of xy dy dx plus, and I'm just rewriting the rest, 2y dy dx is equal to 1. Is this okay so far? Yeah? I just want to make sure. Okay. So again, we want to get these dy dx's here by themselves. So we're going to keep these here on the left. So I'm going to subtract this y secant squared xy over to the other side. Yeah? Once you have only the terms that have dy dx on one side of your equation, then what you do is you factor out the dy dx. So that way we can then divide whatever is still left in that parentheses. So from here on this side, I'm going to factor out that dy dx, which leaves me with x secant squared of xy plus 2y, which is equal to 1 minus y secant squared of xy. And then to solve for dy dx, we're just going to divide by all of this. So this would be dy dx. 1 minus y secant squared of xy over x secant squared xy plus 2y. Ten. Yes. Jeez. Okay. Okay. So again, this is another scenario where you think about what this would look like if you were to plug in infinity and see what would happen. But first, before we do that, right, we have here this e, which is raised to a negative exponent. Anything raised to a negative exponent, remember that that means that it's just in the wrong spot. So that e would move down to the denominator. So this is the same thing as saying the limit as x is approaching infinity of negative 1 over e raised to the positive 3x minus 1. Does that make sense? Okay, now plug in infinity, right? So this is negative 1 over e raised to the 3 times infinity, which is just infinity, minus 1. E raised to infinity, e is an exponential function that is always growing. So if you plug in infinity, you're just going to get infinity. And we already established in an earlier example that if you have a fraction with infinity in the denominator, what does this equal to? 0. Exactly. So this would be 0 and then minus 1, which would just give us negative 1. Four? Okay, so the limit as x is approaching -3 from the left, and this is important because here we have a rational function. And if you were to plug in -3, you would end up with 0 in the denominator, right? Meaning that we have a vertical asymptote, right? So that means that that limit, if it was a general limit, the limit as x is approaching -3, period, not from the left or from the right, it would be does not exist because we have that vertical asymptote there. That's okay. But because it's asking from the left, if you're ever asked for a limit that's either from the left or from the right, it will not be does not exist. It will be something, right? Because it could go up forever, it could go down forever. That's the thing with asymptotes, is that that means that then our function is either going to get infinitely close to the asymptote as it goes up to infinity or goes down to negative infinity. So I already know that my answer is going to be some kind of infinity. Now we just have to figure out which one is it. Is it positive or is it negative? And we figure that out by plugging in a number that is slightly to the left of -3, since it's saying -3 from the left. Okay, so -3 from the left, something slightly to the left, let's just say -3.1. That's to the left of -3. Does that make sense? So we plug in -3.1. So -2 over -3.1 plus 3. With these, all I care about is the sign. I don't care about the actual number because I know that my answer is going to be some sort of infinity because of that vertical asymptote. So we have a negative in the numerator, so the -2, over a negative in the denominator. And a negative over a negative makes it positive. So that means that my answer is positive infinity. Is that all right? Yes, that's right. Mm-hmm. 29? Okay. And then Mackenzie, you were going to say something as well? Okay, so we'll do 29 and then 34. There's 29. Okay. Okay, so this one, basically to find this derivative, um, these were just derivatives, okay? They're kind of mixed in with implicit. I didn't want to like, I know it's a long assignment already. I didn't want to like have separate sections. So here everything is already just in terms of x. So we just have to rewrite this in a way that would make it easier to take the derivative, meaning we want it like in a polynomial type equation. So we want to rewrite those exponents. So we have the 8x to the 6 is fine. I can take that derivative. Now this -5 is being multiplied by the fourth root of x, which if we write the exponent, that's x raised to the 1/4. Is that part okay? Okay, and then this plus 2 over x to the third, that's 2x to the -3. So I just brought that up and made that exponent negative. And now we can take that derivative. So our y prime or dy dx, whatever you want to call it, we just apply the power rule for all of these. So 6 times 8 is 48, x to the fifth, minus 5 times 1/4 is just 5 over 4, x, and then we have to subtract 1. So this is 1 over 4 minus 1, which is 4 over 4, right? So 1 minus 4 is going to be -3 over 4. So that is our new exponent. That doesn't look like a negative, so I'm going to put it up here like that. And then 2 times -3 is -6x, and then subtract 1, so -4. Is that okay? That's basically it. I don't remember how I wrote it in the answer key if I put it all back with positive exponents, which if you were to do that, that would be 48 x to the fifth minus 5 over 4x to the 3/4 minus 6 over x to the fourth. And you can also even still rewrite this x to the 3/4 as x to the third and the fourth root of that. So that is the same as that. Is that okay? And you said 34, right? I already forgot. Okay. Okay. So here, let me see. The rules for finding derivatives of log. Okay, that's what we would need to know. Um, the rule for log when we're finding the derivative of log, that's going to be 1 over the ln of a times, I know that you're probably like, what is what? I don't remember either. I will tell you. No, I remember. U times du dx. Okay. A is the base of your log. U is this, whatever is inside of log. Is this okay? So this is just the derivative rule for any logarithmic equation. Now, if I'm not given a base for log, what is the base? 10. Exactly. So this would be 1 over the ln of 10 times u, which is x squared plus 3x. And then I multiply this by the derivative of u, which is 2x plus 3. So then we just put this together, right? 2x plus 3 is like over 1. You can multiply numerator with numerator, denominator with denominator. So this would give us 2x plus 3 over the ln of 10 times x squared plus 3x. It's a lot of rules to remember, especially with derivatives. I think, I don't remember if I did or not. If I didn't, I'll post it for you. I do have like a flashcard document with all of these derivatives that you can use to practice. Did I ever post that? No? Okay. Do you want that? Would that be helpful? Okay. Let me I gotta write it on my hand or else I'll forget. So just give me a sec. I'll post it. Where do you want me to post it? Google Classroom, website? Google Classroom? Okay. So the way that I have those that document is I if I remember correctly because I did this I think last year, the like one page is the front and then the page following is the back. So you can print it front and back. So that way you have like the derivative rule and then examples. Okay? I think that's how I'll double check. Whatever. Point is you'll have all the information that you could print. Okay? All right. What else you got? 35? Sure. Okay. This is chain rule, right? Because automatically you see trig, you got to think the chain rule. Now this is could be written so that way you can kind of see all of the layers. This is the cosine of 3x squared to the third, right? Because whatever is here, that exponent that's directly after the trig function, that means that the entire thing is raised to that exponent. Is that okay? So now when we take that derivative, right, we got to work our way from the outside in. So we do one derivative at a time, and then we always multiply it with what is on the inside. So the first layer is that exponent of 3. So I apply that power rule first. So this would be 3 cosine of 3x squared, and then squared. You can if you want to. You don't need to. That's up to you. Did I do that? I don't remember. Oh, I did. Do you want to distribute the exponent first? You should get the same answer. Okay. Okay, we'll try it out and see what happens. Okay. Okay, so that's just this layer. So what I like to do, I like to scratch it out just to show I'm done with this layer. Okay, now the next layer is the trig function. The derivative of cosine is negative sine. So negative sine of 3x squared. So done with that layer. Now the derivative of the angle. I'm thinking, because I'm thinking if it makes a difference. Okay. Yeah, you should still be able to get the same answer, because if you look at 3x squared, if you treat it like a chain rule, right? You bring the 2 to the front, you apply the power, so that would be 2 times 3x, and then raised to the first power, and then times the derivative of the inside, which is 3. And that would give you 2 times 3, which is 18. Did you guys catch that? Or if you prefer, apply the exponent first, right? So 3x squared, that's 9x squared. And the derivative of 9x squared is 18x. And then now you just put basically everything together. So the only thing that you can really multiply together is this 18x, the negative, and the 3, which all of that multiplied together is negative 54x. And then we have this cosine that is squared. So we're going to put cosine squared of 3x squared, or you can write 9x squared because it's the same thing. And then times sine of 3x squared, or again, 9x squared. So this is the same thing as this. Thirty-seven. Yes. Okay, so this is inverse of trig, which I know, again, it's been a long time since we've done these types of derivatives. But the rule for your inverse tangent function, the derivative, well, let's call this u instead because we have a function, is u prime over 1 plus u squared. Yeah? That's, again, something to remember, okay, which those flashcards will come in handy. So in this case here, cosine, that's u. So I just make like a list. My u prime, the derivative of cosine is negative sine x. And then u squared would be cosine squared x. And then I just plug it into the derivative rule. So this would be negative sine x over 1 plus cosine squared x. And that would be your answer. That is from the derivative of the angle. Because you know how we're doing layers, right? We did the power first, then we did the trig, and then the last layer is the angle. So 3x squared, that's 9x squared, right? Like if I were to apply that exponent, so the derivative of 9x squared is the 18x. No, I didn't apply it twice. I applied the exponent just to simplify the angle, and then I took the derivative of the angle. You get me? Like when you're applying the exponent to something, whatever is inside the parentheses, you do have to apply that exponent to both the number and the variable. Because it's like saying 3x times 3x. Yeah. 60? Okay. What is this? We're just integrating, right? Okay. Okay, so here what we have is x squared minus x plus 4 over the cube root of x, which in order to integrate this, so with integration, I mean, there's a plus and a minus, right? The plus side is that there are not a lot of rules for us to have to memorize, unlike derivatives. But the minus side is that you do have to get a little bit creative when you're trying to integrate. We do know how to integrate polynomial functions because that's easy. Just add 1 to the exponent and divide by the new exponent. However, this is not a polynomial type function, but we can rewrite it so that it is. This is all, and here's how I know to do this. If I have a polynomial type function divided by one term, right? This is only one term, one thing. That means that I can divide everything in the numerator by whatever is in the denominator. So I'm going to rewrite this as the integral of x squared minus x plus 4, and it's all over x to the 1/3. So far, so good? Okay, now what we do is we basically do x squared divided by x to the 1/3, x divided by x to the 1/3, and 4 divide, like I'm dividing every single term by x to the 1/3 in the numerator. So wherever you have the x's, you just subtract. So this is 2 minus 1/3 to get the new x, which 2 minus 1/3, we have to put this over 3. So this is 6 over 3 minus 1/3, which is 5 over 3. Is that okay? So that's just this with this. Okay, now minus. Now we have x over x to the 1/3. So here my exponent is 1, so I'm going to subtract 1 minus 1/3. So this was 3 over 3 minus 1/3 is 2/3. So this is x to the 2/3. And then this is 4 over x to the 1/3, which we don't have to divide anything. This would just be plus 4x to the negative 1/3. Does that clear that part up? And now we apply the power rule. So for all of these, we add 1 and then divide by the new exponent, which everything has a denominator of 3. So adding 1 would mean to add 3 over 3. So x 5 over 3 plus 3 over 3 is 8 over 3. And then we have to divide by the new exponent, which if our new exponent is a fraction, that means just multiply by the reciprocal. And the reciprocal of 8 over 3 is 3 over 8 plus, minus x. This is 2 over 3 plus 3 over 3 is 5 over 3. Then multiply by the reciprocal, so 3 over 5 plus 4x, and then negative 1/3 plus 3 over 3 is 2 over 3. And then I'm going to multiply that by the reciprocal, which is 3 over 2. And now we just simplify, which the only thing to simplify is this term here, the 4x to the 2/3 times 3 over 2. So our final answer would be 3, 8 times x to the 8 over 3 minus 3 over 5, x to the 5 over 3. This becomes 2, and then 2 times 3 would be plus 6, x to the 2/3 plus c. Mhm. What else? Any other questions? 17. Sure. Determine whether each function is continuous at the x value where the function has a possible point of discontinuity. Use the three-part definition of continuity to justify as to your answer. Okay, so the three-part definition of continuity. Does anybody remember what the first part is? That's the second part. That's correct. But what's the first part? F of A exists. Perfect. Then 2 is exactly what you said. The limit as x is approaching a from the left of f of x must equal the limit as x approaches a from the right of f of x. And what is the third part of the definition of continuity? Exactly. The defined value is equal to the general limit value. So that's what we're going to do first. The possible point of discontinuity is where your piecewise function splits, which you see here in your inequalities. Our piecewise function splits at x is equal to -1. So a in this part of our definition is -1. So we want to check to see if it exists, which it does, right? It exists here on the bottom equation because we see here that our inequality, it says that x is greater than or equal to -1. So to find f of -1, we plug it into the bottom equation. So 2 times -1 plus 3, that's -2 plus 3 is equal to 1. So that is our defined value. Now we need the limit from the left and check it if it equals to the limit from the right. The defined value, this is also equal to the limit as x is approaching -1 from the right of f of x, since this is for also when x is greater than -1. So what we're looking for now is the limit as x is approaching -1 from the left, which is where we plug it into the top equation. So we have negative -1 plus 2 squared plus 2. -1 plus 2 is 1. 1 squared is 1. We have its negative. So -1 plus 2, which is 1. So we have here that the limit from the left equals the limit from the right. Therefore, the general limit is also equal to 1. So for part 3, my f of -1 does equal to the limit value as x is approaching -1, which is 1. So therefore, f of x is continuous at x is equal to -1. This symbol, by the way, the 3 dots like in a triangle, that means therefore in math, if you ever wanted to use that. But be careful because this means therefore, and if you do it backwards or upside down rather, like the triangle facing down, that means because. If you ever care about those symbols, there it is. Okay, I have time for one more because I do have an appointment. Should be fine. Sure. Okay. Okay, a spherical weather balloon is being inflated at a rate of 600 cubic centimeters per second. At what rate is the balloon's surface area changing if the radius of the balloon is 20 centimeters? Okay, so here what we're given, do you know what this represents? What was that? dV dt, exactly. First of all, this is a rate because it does say a rate. Also, if you look at the units, you have your unit of measurement over time, so that if they didn't say it was a rate, we would know because of those units. And the centimeters is cubed, so that means it must represent volume. So that's dV dt, which is 600 cubic centimeters per second. Okay. We're trying to figure out the rate of the balloon's surface area. So I am looking for, I'm going to put dSA over dt. That's what I'm trying to find. If the radius of the balloon, so R, is 20 centimeters. Is that okay? Okay. Now, whatever information you're given with related rates, that means you're going to use it. Okay, so we're given this volume or this rate of volume, so that means we're going to have to use that somewhere, even though what I'm looking for is the rate of the surface area. And this is why, right? If I am trying to find the rate of the surface area, this is the surface area equation. The rate, if I would have to take the derivative to find that rate. So that would be dSA over dt is equal to 8 pi r times dr dt. Yes? Now I have the radius, but my problem is that I don't know what dr dt is. And that's why we were given this, because that must mean that we can use dv dt to solve for dr dt. So we're going to come here to the volume. Volume is equal to 4 over 3 pi r cubed. So if I take that derivative, dv dt is equal to 4 pi r squared dr dt. I know dV dt was given, which is 600, is equal to 4 pi r, which was also given, which is 20 squared. And then I can use this equation to solve for dr dt. Okay, so 20 squared is, was that 400 times 4 is 1600. So we have 1600 pi dr dt. So to solve for dr dt, we're just going to divide by this 1600 pi, which now we can simplify. So I can get rid of these two zeros. So we have 6 over 16 pi. And then I can divide both of these numbers by 2. So this is 3 over 8 pi. So that's dr dt. Is that part okay? Now I take this and I plug it in for dr dt, and I also can plug in my radius. So, because remember, I'm solving for the rate of the surface area, which is going to be here 8 pi times the radius, which is 20, times dr dt, which is 3 over 8 pi. The 8 pi's will cancel, and we're left with 20 times 3, which is 60. Our units, this is surface area, so that would be centimeters squared per second. Sure. Mm-hmm. That's when you know you're maximizing or minimizing by if you do your number line, right, to check the critical number. Like if I were to find the x or whatever for 51, if I use the derivative and I create my number line, I should get that it goes from negative to positive, indicating that it's a minimum, and that's how I know I'm minimizing. Well, if that happens, either it cannot be maximized, right? Or maybe there's another critical number you missed, or there's just no answer. But typically, like whatever they ask for, that's what you're gonna get. Like it's not meant to be a trick question. Do you get what I'm saying? Okay, I guess that's it for today. I know that I see you guys on Monday, right? What I'll do if you have any more additional questions like after this, like maybe you haven't finished your assignment yet, so you're not quite sure like what else you have questions on. On Monday, I think I have it so that we have a lesson on Monday, right? I can't remember. It's already been a week, so I don't know. Just remind me and I'll take questions at the beginning. Okay? So that way, in case if you have any last minute questions, I'll go over that. But I will save this video and upload it also on Google Classroom for you guys in case you need to like review any of the questions that we did go over. Okay? All right. Thank you so much, guys, for joining me. I know it sucks so early on a Saturday, but I do appreciate it. Okay, so I will see you on Monday. Enjoy the rest of your weekend. Yeah.